So we're going to pick up in chapter 5. We're going to talk about waves, motion, and sound. Our chapter outline, we're going to talk about forces and the nature of materials. And so we're going to focus on elasticity specifically. Then we are going to describe vibrations, waves. Then we're going to define waves, discuss types of waves, waves in the air, how we hear waves, sound waves, then boundary effects, interference, loudness, resonance, sources of sound, and then we're going to talk about moving sources and how they behave a little bit differently than a stationary source. So when we're talking about an applied force to an object, there's something that's really important that we have to consider called elasticity. When a force is applied to an elastic material, it's going to behave differently than if that material was inelastic. So what's the difference between the two? Something that's elastic would be capable of recovering its shape after being deformed. So after the force is applied and that force is then removed, it would return to its normal shape. An inelastic material is not capable of that. So whatever external force is applied is basically going to destroy the original shape of the object. We have 4 images here. We have clay, a spring, a plastic bottle, and a rock. So take a moment and make a prediction. Which are elastic and which are inelastic? And write them on your notes, and then we'll see if you're right. Okay, so let's think about this. If I apply a force to any of these 4 objects, which ones are going to absorb the force and then return to its shape? Well, obviously the spring is. If I push or pull, so push or pull on the spring, we know that when that push or pull force is removed, it's going to come back to this shape we see here. So this would be elastic. Now the water bottle, we know plastic tends to be inelastic. That's kind of the nature of plastic. It's really easy to break, really easy to deform. And so because the plastic water bottle can be crushed and it's not going to return to its nice bottle shape that it had before, it's inelastic. Now clay, while clay is moldable and it can be shaped, it does not return to its original shape when the hands are removed. Like for instance, when you start off with clay, you kind of start off with a lump of clay and you put water and you start molding it. But this cup is not going to turn back into the block just because the person stops molding it with their hands. It's going to stay there in the shape of what they're molding. So it is also inelastic, though it is moldable. The last one is the rock, and this is kind of looking forward into earth science, which we're going to talk about stress and strain that rocks will feel. And in this case, rocks are going to be inelastic because when they have a force applied to them, either the earth, another rock, wearing agents, erosion agents, it's going to break the rock, but the rock is never going to be returned to its original shape just because the force is removed. So it's going to be inelastic. Okay, so hopefully you got those defined correctly. Some other examples of an elastic material would be a rubber band, a scrunchie, a rubber ball. Those are all examples, a tire, of things that are elastic in nature. So the reason why it matters about whether something is elastic or not is that our elastic materials are going to be the ones that tend to produce vibrations. A vibration requires 2 things. There must be a back and forth motion, and it must repeat itself. So for instance, if I have a spring here, and this is at rest, so this is with no pushing or no pulling, and there's a block on there, and on the block there's a pencil. And then all of a sudden I'm going to pull the spring down. It's like loading a bow and arrow, pulling the bow all the way back before you release the arrow. So I'm going to pull this block all the way back, and then I'm going to release it. And what's going to happen is the spring isn't going to just jump back and stop at rest. No, it's going to go up further past rest. Then it's going to come back down. Then it's going to go back up. And then it's going to go back down. And eventually the spring over a period of time will come and will stop back at rest. Okay, but not before it does this sinusoidal wave type shape that is a back and forth motion repeating itself. So the repetition is here and here. Okay, it's not going to go back, back, forth, forth. It's going to go back and forth, back and forth. So we're going to describe vibrations, but when we're describing the vibration, we are also describing waves. Okay, they're going to have the same exact definitions and features. Okay, so we're going to talk about them together. So the first important definition is the amplitude. The amplitude is often called the intensity because it's going to be the height of the wave, how high up it goes. Okay, so that's amplitude. And amplitude is the same between, this is at rest, between the rest in the amplitude, or in point A, and the rest in point C. Okay. Now you see here there are ones that are important, the crests and the troughs. These are the high points, and these are the low points. And then we're going to have a couple of other important parts that are going to be defined. We'll use between the points that we have on our graph. So the cycle is going to be one complete vibration. It's starting at one point and then returning to that same point. So between point A and E, this is going to be one cycle. It starts up here at the top of the crest, goes down through the trough, comes through rest, and stops again at the crest. So there could be lots of cycles. You could define it as point C down here all the way across. It could be from D to G, but the point is it's going to make that full back and forth motion. Now the period, just like you had periods in school, the period is going to be the amount of time, usually in seconds, for one cycle. So this is timing it. Okay, it's past point A, I'm going to time through point B, C, D, E, stop. Okay, so a period is the time. Now the next one is frequency. And this is specifically related to time as well, but it's the number of cycles that occur per second. So waves that look like this versus that, you can see that there are going to be more waves on this top one per second than the bottom one. So this would be a higher frequency, and this would be lower frequency in the bottom. And that's because the wave is more frequent. It's the same thing as if you have, if you're at the beach and water is coming into shore, very fast waves coming in, that's a high frequency wave, versus if you only have a wave coming in every, few seconds, it's a low frequency wave. Now the wavelength is also going to be related to one cycle, but it's the length in meters of one cycle. So if you could take a meter stick out there and measure the height of the length of one cycle with the meter stick, that would be what we're talking about right here. So the last four, or the last three of the four, are all related to one cycle. All right, so what this brings us to is a wave. There are two causes of a wave. The first is that there is a period motion disturbing the surroundings. And the second is a pulse disturbance of a short duration, which is what we see here. A rock being thrown into the pond is a pulse disturbance of a short duration. What we talked about on the last slide, the period motion disturbing the surroundings, the spring coming back and forth, that's the first one. Okay, so two different types of scenarios will cause a wave. Now, a wave is defined as a periodic or traveling disturbance that transports energy. Okay, so transporting energy means that it's capable of doing something. It's capable of being detected, capable of producing sound and things like that we're going to talk about. Okay, so two causes of a wave, and then the definition. Now there are two different types of waves. The first type of wave that we're going to talk about is called a longitudinal wave. And this is where the vibration direction is going to be parallel. So remember, parallel, we use a symbol like that, to wave propagation. So it's kind of whether you push or pull is going to be in the same direction that the wave exists. And then particles in the medium will move closer together or further apart. And the most common example of a longitudinal wave is a sound wave. So you'll see here, it looks kind of like where you see the parts are further apart and then closer together. So this is where they're saying these are further apart and then these particles are closer together. Okay, but the propagation is meaning how we start. If I pull the spring, it's going to be in the same direction of the wave. And I'm going to post a video that you need to watch that will show you using a spring. It's really great. It's about 2 minutes long, and it does a great job of describing the difference between longitudinal and transverse. So this is our second type that we're going to talk about, which is a transverse wave. The vibration direction is going to be perpendicular to the wave propagation. And the best example is a plucked string. So if you have a stringed instrument and you pluck it with your finger, you're going to pull back this way, but the wave is going to propagate out that way. Okay, and so you can see it's perpendicular. The force is this way, and the wave is going to be perpendicular to that. Okay, so you're going to have a YouTube video to watch, 2 minutes, and it will explain the difference between longitudinal and transverse. The next thing we're going to talk about is what happens with waves in air. That is the most common medium that we have because we live in a world that's full of gaseous molecules. Therefore, air is transporting our sound through the air to be heard by your ear. There's another way we could probably physically feel it. If you swing a door back and forth, so you're standing at a door and you open, shut, open, shut, open, shut, it's going to be a vibrating object. That vibrating object is going to produce what you will perceive as very hard wind and then like no wind. You'll feel the wind come towards you, the wind go away, the wind come towards you, the wind go away. What happens is it creates a pulse where you're going to have low parts, high parts, low parts, high parts. Okay, so it's going to look just like the wave we talked about with the longitudinal. Now what's happening here is the molecules are condensing together, which we're going to call condensations or compressions. And then in the low parts where the molecules are very far apart, they're called rarefactions, which I know I just wrote over that. But they're going to be alternating areas of condensations or compressions and rarefactions. There's not a lot of molecules in the rarefactions, and then there's going to be a condensed, compressed area in the high parts. So this is how we hear. Okay, this is what your ear is hearing. So your ear is made up of 3 regions. You have your inner ear, your middle ear, and your outer ear. Your outer ear is going to be all the way from kind of the part that your ear lobe, all of the parts outside. It's going to go into the ear canal. The external part. So that's even though this image looks like it's very big, it's actually not a very long ear canal. Now, the transition between your outer ear and your middle ear is defined by the tympanic membrane. So it's kind of like a timpani, if anybody ever was ever in band and knows that. But it's going to be marked by essentially your eardrum. So when you have a ruptured eardrum, when you have an ear infection, fluid behind in your middle ear, it's going to be held behind this eardrum, and it's kind of just like a film. Now, the middle ear is going to go all the way in to where you have some of your hearing parts. You're going to have your eustachian tubes. These are often what gets infected in little kids, an inner ear infection. And then you have a really important feature called the cochlea, right here. Looks like a little shell, which is attached to your auditory nerve. Now, when you are hard of hearing or deaf and you have sometimes you get what's called a cochlear implant, which helps replace the cochlea, which is malfunctioned. But what happens is as the waves travel into your ear, they hit the membrane. The membrane is attached to these little bony features, and the bony features vibrate. And that vibration is detected by the cochlea, which is then transmitted to the auditory nerve, which is how you hear. So when you have an ear infection, sinuses, anything like that, it is so hard on this part of your ear, which is why you hear less. Everything sounds stuffy. Sometimes long-term damage can come from ear infections, and you can become hard of hearing or deaf in one ear because of inflammation inside this part of your ear. So the normal range of human hearing is 20 to 20,000 hertz, which is pretty big, pretty wide. Now that's just normal. So if you have high frequency or low frequency hearing loss, your range is not going to be the same. When we have something that's less than 20 hertz, we're going to call that infrasonic. And these are things that you can feel, but you don't necessarily hear them as much. So sometimes with really loud bass in cars, you can hear the vibration, but that's infrasonic. Very low, like loud booms, things like that can produce the low frequency infrasonic noise. Now, ultrasonic is the other side. This is 20,000 hertz and higher. Normally, the animals that hear this are the dogs, the cats, rats, bats, and we use it in imaging. So the thing about the high frequency hearing loss or high frequency noises is that they're so high pitched that we don't actually, the structures in your ear are not fine tuned enough to perceive them. So some people can hear them because their structures work really well, and other people can't, but it's not abnormal to not be able to hear them. So sound waves require a medium for transmission, meaning sound does not transport in a vacuum. You have to have a solid, a liquid, or a gas. Now, the speed at which the sound travels is going to depend on the inertia of the molecule, which is going to be, if you think of inertia, when we talked about our chapters of physics, inertia is the ability to resist motion. Then interaction strength and temperature. So we can see here there's a couple of examples of medium. So carbon dioxide, dry air, and helium, all at 0 degrees Celsius. The only difference here is the weight. So carbon dioxide weighs more than just regular old oxygen, which weighs more than helium. And as the molecule becomes lighter, and even hydrogen, which is still less than helium, the speed of sound is going to increase. Okay. And when we start thinking about things like water versus seawater, we can see that the speed of sound is roughly the same. And then when we start talking about lead, glass, and steel, these are our solids. And the sound is going to transmit even faster through steel, glass, and lead than in regular air. Okay, so we're going to take a break here. Make sure you go and watch the YouTube video about the longitudinal and transverse waves with the slinky or the spring. I guess it's kind of both, but go watch that video and then come back and finish chapter 5.